Okay, in this lesson, we're continuing to look at the circular motion of a charged particle injected into a magnetic field. And to give us a little more practice with slightly different perspectives, I've changed the B field to be into the paper. And the charged particle itself is still injected perpendicular, but now it's positive. So the V vector is in the plane of the page, so we have our positively charged particle with a velocity vector, which I'm going to say is V perpendicular, because it is perpendicular to the B field. So once we get into the B field region, I'm just drawing it out here to illustrate the point, we get QV cross B, so we get our magnetic force as shown there to the right, straight up, and please take a moment to do your right hand rule to convince yourself that's a thumb up, but more importantly radially inward in this problem. And for the circular motion problems we're looking at initially with the magnetic field, we're restricting ourselves to 90 degrees. We will stop doing that in the future and go to other than 90 degrees. But for right now, we have only 90 degrees, so we only get this perfect circular motion in the plane of the page. To give you an idea of what would change if we did add something other than 90 degrees, that would be like giving it a velocity in addition, into the paper or out of the paper. So let's say the particle was spinning in the plane of the page, as we have here, and you like tapped it, plink, and gave it a velocity into the page. Well, it would still continue to spiral, but now it would also have this additional velocity parallel to the B field lines. So we would get, in that case, sine of 0 degrees, so there'd be no magnetic force, so it would be just circling and spiraling away from you. And again, that's just a peek ahead. We'll talk more about that later. So for right now, perfect circular motion in the plane of the page. QV cross B, sine is 90 degrees. QVB equals mv squared on r. The QVB is the radially inward force, the lasso, if you want to think of it, holding the particle in circular motion, just like the tension in the string would hold the particle, a ball spinning in a circle, back in mechanics, and that equals our mv squared on r, Newton's second law. F equals ma, so we get qvb equals mv squared on r, and the acceleration is v squared on r, and when we bring the m down, right, we get the v squared on r equals qvb on m. So now we have an equation that we can use to help us problem solve. And when you're asked questions about changing the speed or changing the radius of the particle, you definitely want to go to this equality. And in that case, you can see we have a v, and one of the v's cancels out. So as long as the B field doesn't change, the Q doesn't change, and the particle itself doesn't change, QB on M is constant. So if we change the velocity, the radius has to change as well. So if V gets bigger, R gets bigger. If R gets smaller, V gets smaller. So in addition to this analysis, which you definitely would have to be able to derive either of these equations. Let me clean it up here. So either of the equations, the purple QVB equals mv squared on r, or the centripetal acceleration, you are going to have to remember some of our circular motion equations that are other variables. So if speed equals distance over time, the distance traveled around the circle is 2 pi r. Period of motion is the time to go around the circle once, capital T. Remember the relationship between period of motion and frequency is that they are reciprocals. So period of motion is in seconds. Frequency of motion is 1 on seconds, which equals 1 hertz. So recall that. They can also phrase the questions now in terms of angular speed. So we have v squared on r in our green equation up here. So we have v in that equation, so that v tan equals omega r. We have omega equals 2 pi f, angular frequency. The omega is the same thing, it's just the language we use in the questions. And to give you practice with the type of questions you might be looking at using these equations, I have some practice for you. Now, I do want to have you keep in mind when doing this that you are using a positively charged particle. You are given the speed. You are given the magnetic field in the x direction. In part A of this problem, you are also given the force, and you are asked to calculate the angle. So here, at first, we are not assuming we have V perpendicular only. So you are going to use FB equals QV cross B, and use the sine of the angle to get your angle in part A. And then you'll be looking for the looking at the cross product for answering B. But now this is the important part. For C on, for all of the rest, make sure that now we are changing the velocity vector to being V perpendicular only, and answer the rest of the questions based on V perpendicular only. And I will leave you to do that. You can pause the video here, and when you unpause it, I will show you the solutions. Okay, hopefully you have tried these on your own, and if you look at the solutions here, you can freeze the screen. Take a look at what is here. It is really important that you understand every single one of these questions, A through I. And if you have any questions at all, we need to go over them in class. You need to ask.